Hello, welcome to another module in this massive open online course. So we are looking at quantization and we have started looking at uniform quantization. Alright, we looked at various aspects of quantization. Quantization converts an analog sample value, alright, maps an analog sample value to a discrete set of values, alright, which can be represented by bits to be transmitted over a channel or for storage. We have started looking at a uniform quantizer with an odd number of quantization levels, odd number of quantization intervals, which results in a mid-thread quantizer. So let us now look at a uniform quantizer with an even number of quantization levels, alright. So we are continuing to look at uniform quantization. Previously we have seen uniform quantization with an odd number of quantization levels. So let us now look at uniform quantization with an even number of quantization levels, okay. And therefore uniform quantization with an even number of quantization levels, okay. Let us say we consider four quantization levels and therefore we will have a quantizer. Consider four quantization levels, comma, and quantization interval of width delta, okay. Let us write that quantization interval along with a quantization interval of width delta, okay. So therefore we will have four quantization intervals, each of width delta. So naturally they will be from 0 to delta, delta to 2 delta, minus delta to 0, minus 2 delta to minus delta. These are our four quantization levels, and of course in 0 to delta, if you are considering uniform quantization, therefore you are mapping it to the midpoint, that is delta by 2, okay. So you are mapping it to, let us say this is your delta, this is 2 delta, this is minus delta, this is minus 2 delta. So we are mapping it to delta by 2, and then delta to 2 delta you are mapping it to 3 delta by 2, okay. So this is basically delta by 2, 3 delta by 2, and of course in minus delta to 0 you are mapping it to minus delta by 2, minus 2 delta to minus delta you are mapping it to minus 3 delta by 2, okay. So basically this is your delta by 2, this level is basically 3 delta by 2, this is minus delta by 2, and this is minus 3 delta by 2, alright. And therefore naturally you can see that in the middle, that is at, if you look at it in the middle, that is at 0, right. So if you look at it in the middle, that is at 0, correct, we have the quantizer characteristic which is rising at 0, alright. Therefore it rises from minus delta by 2 to delta by 2, therefore this is known as a mid rise quantizer, alright. So we see when we have an even number of quantization levels, the quantizer characteristic rises at delta equal to 0 from minus delta by 2 to delta by 2 in a uniform quantizer with an even number of quantization levels. This is termed as a mid rise quantizer. So in a uniform quantizer with an even number of quantization levels, in a uniform with even number, that is with an even number of quantization levels, the quantizer characteristic rises from minus delta by 2 to delta by 2 at x equal to 0, or basically the input equal to 0, or at m equal to 0. This is therefore termed as a mid-rise quantizer. That is, this is therefore termed as a mid rise. This is therefore termed as a mid-rise quantizer. This is therefore a mid-rise quantizer. It rises in the middle. The middle is at m equal to 0. It rises from minus delta by 2 to delta by 2. Therefore, this is termed as a mid-rise quantizer. So, we have two different kinds of uniform quantizers, one with an odd number of quantization levels, which is flat in the middle at delta at m equal to 0, that is a mid-trend quantizer. A uniform quantizer with an even number of quantization levels, in which the characteristic rises from minus delta by 2 to delta by 2 at m equal to 0. This is termed as a mid-rise quantizer. Okay. Now, let us also look at some other aspects of quantization. For instance, we have delta equal to the step size, that is also the basically this is also your quantization interval. This is also known as the step size of quantization. This is also known as the quantization interval. Okay. So, you can think of this as the quantization interval length. Or basically length of the quantization interval. Step size is basically the step from one quantization interval to other, or basically one quantization level to another. Alright. So, this is the step size delta, and this is uniform in a uniform quantizer. Okay. Now, let us say the number of levels equals, now let us say signal m spans from, well, let us say spans from minus m max to m max. So, this is your maximum amplitude, or peak negative amplitude, let us put it that way. And we are assuming to be symmetric, and this is your peak positive amplitude. M max is your peak positive amplitude, and let us say, so therefore, total interval, therefore, total quantization interval, therefore, total width of quantization interval, or we can say the dynamic signal range. So, total quantization interval or basically your dynamic signal range that is equal to twice m max. Okay, m max minus m max, that is twice m max, that is the total dynamic signal range, that is the width. Right. Now, this is being quantized with quantization interval, that is quantization step size delta, which means, so now, so therefore, you have twice m max, this is your dynamic range. So, you have minus m max over here, you have m max over here, and you are dividing this into uniform intervals of width delta. This is your step size. So, naturally, this implies that the number of levels, that is number of quantization levels equals number of intervals equals 2m max divided by delta. So, let us say number of levels L. Okay. So, let us say the number of quantization levels L which are element of this discrete set, we have L equals 2m max by delta for this uniform quantizer. Okay. Okay. So, so L equals to 2m max by delta, or alternatively this implies also that this also means that delta equals 2m max divided by L, that is the width of the interval, that is the step size is twice m max, the dynamic range, divided by the total number of quantization levels. Okay. That is the width of each uniform interval. Okay. Now, let us look at the notion of quantization error. Okay. And this is a very important metric which determines the performance of the quantization of the quantizer, which is the quantization error. So, we have said that all samples in a particular quantization interval, correct, a particular quantization interval are mapped to a particular quantization level, which is a many to one mapping, all right, which means there are several values which are mapped to an approximate quantization level. Therefore, there is going to be quantization level, all right. So, quantization is a many to one mapping is a many to one mapping in which all sample values in a particular interval are mapped to a quantization level. This implies that there is error. Well, there is an approximation error. Quantization is nothing but approximation, correct, which is basically your quantization termed as the quantization. There is an approximation error in this approximation, which is termed as, this is termed as quantization error. This is termed as quantization error, all right, because we are mapping a large number of samples, approximating them by a single quantized value, that leads to an error, that is termed as quantization error. And the context of uniform quantization, we have already seen that, for instance, if you look at the quantization interval 0 to delta for the previously considered quantizer with even number of quantization levels, all the samples in sample values in 0 to delta are mapped to minus delta by 2. So, naturally if the sample is 0, we will have 0 to delta are mapped to delta by 2. So, naturally if the sample is 0, we are going to have a quantization error, right, which is basically the quantization level minus m delta by 2 minus 0, which is delta by 2, or if it is delta which is mapped to delta by 2, then we are going to have a quantization error of delta minus 2 to minus delta, which is minus delta by 2. So, basically you have a quantization error which spans, right, for every particular interval, which spans from minus delta by 2 to delta by 2. So, in a uniform quantizer, quantization error, the quantization lies in minus delta by 2 to delta by 2, correct. For example, consider the interval 0 to delta. Okay, the quantization level, corresponding quantization level equal to the equals the midpoint, that is equal to delta by 2, implies the error equals, well, delta by 2, where we say error equals, let us say we denote the quantization, the error equals delta by 2, that is your q of m minus m. So, q of m is delta by 2 minus m is 0, if m equal to 0 and error equal to minus delta by 2. So, this is our definition of error, quantization error, q of m minus m. If m equal to 0, this is delta by 2, is minus delta by 2, if m equals 1 or basically close to 1, it is minus delta by 2. So, the quantization error can be defined as your basically q equals q of m minus m, that is your quantization error, that is q of m is the quantized sample value, m is the actual, the true sample value, m is the true sample value. So, q of m is your quantized sample value, this is your m equals your true sample value. M equals your true sample value. Okay. And therefore, we have seen that q lies between minus delta by 2 to delta by 2. In particular, a simple model can be developed by assuming the quantization error to be uniformly distributed between minus delta by 2 to delta by. So, to develop a simple model for the because this quantization error is random, right, depending on what is the actual sample value, it can lie anywhere between minus delta by 2 to delta by 2, but the probability with which it takes value in any particular range in minus delta by 2 delta by 2 is a random quantity, alright. So, to make things simple, we are assuming that this quantization error is uniformly distributed in minus delta by 2 to delta by 2. So, to make things simple, we are assuming quantization error is uniformly distributed in minus delta by 2 to delta by 2. Error, let us say this is your q, this is your q, this is the probability density function f. So, quantization error is uniformly distributed in minus delta by 2 to delta by 2, the interval minus delta by 2 to naturally the height of this uniform pulse, that is this uniform probability density function, is 1 over delta, that is 1 over the length of the interval. Okay. Height is equal to 1 over delta, okay. That is a probability density function, 1 over the length of the interval. Okay. So, therefore, if you look at the area under this curve, 1 over delta into delta, it is what? So, height equal to 1 over delta, area under PDF. So, height equal to 1 over delta equal to 1 over delta implies area under PDF, that is total probability equal to equal to 1 over delta into delta equal to 1, which is the property that the PDF is satisfied. And therefore, and by the way, f of q, this is equal to 1 magnitude of q less than or equal to delta by 2, sorry, this is equal to 1 by delta magnitude of q less than or equal to delta by 2, 0 otherwise. Okay. And f of q is, this is termed as the probability density function, this is your probability density function of the quantization error. This is the probability density function of the quantization error. Okay. So, it is a uniform probability density function in minus delta by 2 to delta by 2, which means it has height of 1 over delta in minus delta by 2 to delta by 2, all right, and f of q is basically the probability density function, which is a uniform probability density function. Okay. Now, let us see what is the power or the variance of the, now obviously if you look at the mean, now one can see of course from symmetry, that is minus delta by 2 delta is uniformly distributed, therefore by symmetry mean is equal to 0, the average value of quantization error equal to 0, by symmetry average value, that is if you look at this quantity expected value of q, that is 0, which is also defined as, I think you can check this, that is minus delta by 2 to delta by 2 f of q times q dq, that is equal to 0, because this integral, correct, this integral is symmetric, correct. So, f of q minus delta by 2 to, so this is basically the mean, this is your expected value of the quantization error q. Now, we want to find expected value of q square, what is the variance or what is the power of this quantization error of quantization noise. So, we need to find the variance or power of quantization error also termed as quantization noise. Also termed as quantization, and the reason for this being that this quantization causes an error which acts as a noise in the signal. So, you have signal and quantized version of the signal, quantization version of the signal has error that results in noise, right. So, that is quantization noise. Now, what is the variance of this quantization noise? That is basically your expected q square, that is basically integral minus delta by 2 to delta by 2, that is defined as f of q square dq, which is equal to integral minus delta by 2 to delta by 2 1 over delta q square dq, that is equal to basically, that is equal to, that is integral minus delta by 2 to delta by 2 1 over delta q square dq, which is equal to 1 over delta integral minus delta by 2 to delta by 2 q square dq, that is cube divided by 3 evaluated from minus delta by 2 to delta by 2, and that is equal to 1 over delta times twice delta cube twice delta cube divided by 8 into 1 by 3, which is basically equal to delta square divided by 12. So, the power of quantization, so quantization noise power with this uniform distributed quantization noise. So, quantization noise power equals delta square by 12. So, this is our assumption of quantization noise power, that is delta square by 12. Okay. And now, so this is your quantization noise power. So, we have quantization noise, right, the quantization error which causes quantization noise, also termed as quantization noise, that has a noise power delta square by 12. Now, let us look at the, let us again reformulate delta delta equals, well, 2 m max divided by L, which is equal to, well, 2 m max divided by 2 to the power of r, where r equal to log 2 to the base L equals number of bits, alright, because if we have L levels, for instance, let us say we have L equal to 8 levels, we need 3 bits, alright, all possible combinations of 3 bits, 3 binary bits, information bits gives us 2 to the power of 3, that is 8 levels, alright. So, if you have L levels, we need log L to the base 2, that is r bits. So, we need r equal to log L to the base 2, this is equal to number of bits required to represent L levels. To represent the L levels. To represent the L levels, r equal to log L to the base 2. Okay, so r equals number of bits of the quantizer, also termed as quantizer revolution, number of bits of quantizer, that is number of bits output per each sample, number also termed as equal to quantizer resolution. Okay. So, this is also termed as a resolution of the quantizer. This is also termed as a resolution of the quantizer. Okay. Now, we also know that sigma q square, that is a quantization error, sigma q square equals delta square by, well, 12, but we have delta equals 2 m max by 2 to the power of r. So, this is substituting that value for delta, this is 2 m max square divided by 2 to the power of r divided by, well, 12, which is equal to, well, 1 by 3 m max square divided by 2 to the power of 2 r. So, quantization error variance sigma q square, I think we can also write this here, that is your quantization noise power is sigma, so quantization noise power is sigma q square equal delta square by 12. Now, we have sigma q square is 1 over 3 m max, where m max is the peak amplitude of the signal sample, m max square divided by 2 to the power of 2 r. And therefore, now if we take the consider it in dB, quantization noise variance 10 log 10 sigma square, that is equal to, well, minus 10 log 10 3 plus, well, 20 log 10 20 log 10 to the base m max minus 2 r, that is 20 r minus 20 r minus 2 log 10 minus 20 r log 10 log to the base 10, 10 log to the base minus 20 r log minus 20 r, or plus, or rather 2 to the power of 2, L equals 2 to the power of 2 r. So, divided by 2 to the power of 2 r. So, sigma square minus 20, yeah, 20 r log 10 to the base 2. Now, log 10 to the base 2, we know this is equal to 3. So, this is basically you can write this as minus 10 log 3 to the base 10 plus 20 log m max to the base 10, correct, minus 20 into 3, that is basically minus 20 log 10 to the base 2 to the base 10 is approximately 3. So, minus 20 into 3 minus 60 r, this is your noise power. So, if you look at this, this is the noise power. So, you can see the noise power decreases by, so you can see that the noise power, alright, the dB noise power decreases by 60 R, that is for each additional noise bit it decreases by 60 dB. So, dB noise power. So, let us look at the quantization noise variance, that is sigma q square is 1 over 3 m max square divided by 2 R. Now, let us look at the quantization noise. This is the quantization noise variance in dB, this is the quantization noise variance that is 10 log 10 sigma q square, we have said that is equal to minus 10 log 10, that is 10 log 10 sigma q square equals minus 10 log to the base 10 3 plus 20 log to the base 10 m max minus 20 log 20 r, alright. So, when you take log of this factor 2 to the power of minus 2 to the power of 2 r in the denominator, which becomes 2 to the power of minus 2 r. So, that gives us minus 20 r log 2 to the base 10. Now, 10 log 2 to the base 10. So, I can write this as basically 20 log r to the base 20 log 20 r log to the base 20 log. So, 20 r log 2 to the base 10 equals, well, that equals 2 r into 10 log 2 to the base 10 into 10 log 2 to the base 10, and 10 log 2 to the base 10 is 3 dB. Okay. So, this is basically your 3 dB. So, this is equal to 6 times r. So, we have here a factor minus 6 times r. Now, therefore, the noise variance, you can see that this noise variance sigma square dB noise variance decreases by a factor of 6 dB, alright, decreases by a factor of 6 dB for each additional bit. That is, when r increases by 1, alright, minus 6 r, which is the noise variance, decreases by a factor or decreases by minus 6. That is, the noise variance decreases by minus 6. Therefore, the signal to noise power ratio improves by a factor of 6 dB. So, SNR, signal to noise power, signal to quantization noise power ratio improves by a factor of 6 dB for each bit or for each additional bit. For each additional bit. And therefore, what we have is that looking at this expression, correct, when looking at this expression and you look at this term minus 6 r, you will realize that for each additional bit the dB noise variance, dB quantization noise variance decreases by minus 6 dB. Therefore, the signal to quantization noise power ratio improves by a factor of 6 dB for each additional bit, that is for each additional bit in the quantizer, that is as the quantizer resolution increases by 1 bit, alright.